Hi there, welcome to a quick video tutorial on equivalent resistance. If you're in the grade 11 physics class, this is a follow-up to a lab that we did on Kirchhoff's laws that's going to analyze sort of the follow-up conclusion that we made about resistances in series and parallel. So one of the conclusions we made was that if you add a resistor into a series circuit, the more resistors you add, the higher the equivalent resistance is. That makes sense if you think about like a bunch of gates. If you have a big crowd and if you put all these gates in a row, it's going to slow down the flow of traffic through those gates. If you think about a parallel circuit and you think about sort of like an amusement park, if you add gates beside each other and you've got this big crowd trying to get through the gates, the more gates you add, the quicker the traffic's going to flow. They've got more opportunities to go through a gate. So as a result of that conclusion, equivalent resistance, the more resistors you connect in parallel, the less your equivalent resistance happens to be. So those are two conclusions that we made in the lab represented in equation form. So what I want to do quickly is go over a couple of problems involving these equivalent resistance formulas. The first one deals with four resistors that are connected in series. You can see the resistances are given here. What I've done is I've simply taken the R series formula, I've substituted my resistances. This one's pretty simple. You just simply add them together and you end up with your equivalent resistance. So that one's not too complicated. What does get complicated for some people is when you connect resistors in parallel, you're dealing with fractions. Some people are terrified of fractions. What I'm going to do is show you how to do this one quickly on the board. So I'm going to show you that now. So in this example, we know that our resistors are connected in parallel. So what I've done here is I've grabbed the parallel resistance formula and I've simply subbed in the individual resistances for each resistor into the formula. So as you can see here, I'm adding three fractions. For some people, this is where it gets a little bit scary because you have to do a little bit of math. In order to effectively do this, I need to find a common denominator in order to add my fractions, and you can think back to when you learned about fractions in grade 5 or 6. In order to do this, what I've done here is I've written out the factors of each of my denominators. So 10, 20, 30, 40, 50, 60, and I've done that for each denominator. And as you can see, eventually, each of these have 60 in common, so I can get 60 from each of those denominators. So what I want to do is then come over to my fractions, and I want to multiply both the top and the bottom by some number so that I end up with 60 in the denominator. Once I've got 60 in the denominator, I'm able to add those fractions together. Okay, so that's what I'm going to do next. I'm going to look at 1 over 15. In order to get 60 in the denominator, I would have to multiply 15 by 1, 2, 3, 4. Okay, so I'm going to then have 4 over 60. If I multiply 1 by 4 and 15 by 4, I have this new fraction. And you can check this fraction is the same as this fraction. Okay, with the second fraction, 1 over 12, I want to take some number, multiply it by 12 to get 60. In this case, 1, 2, 3, 4, 5 12s would give me 60. So I've got 60 on the bottom. I'm going to multiply 1 by 5. I've got 5 over 60. And the last fraction, to get 60 on the bottom from 10, I would need 1, 2, 3, 4, 5, 6 tenths. I'm going to simply multiply the top and the bottom by 6. Okay, so you can see I've now got common denominators for each of my fractions. This allows me to add my fractions. And if you think back to when you first learned how to add fractions, you can simply add straight across in your numerators, keeping your denominators the same. Okay, so I've got 60 on the bottom. I've got, 15 on top? Yeah. Okay, so I've added my fractions together. I'm now in a position where I want to solve for our parallel. Our parallel is on the bottom. So what I can do is take these fractions and simply flip them so that our parallel is now on top. I've got 60 over 15 on the right-hand side. This is just a simple fraction, which I could actually reduce. 60 divided by 15, we know is 4. Because we're talking about resistance, it's important to put our omega symbol for ohms. Okay, so I've now calculated the equivalent resistance for my resistors connected in parallel. All right, so now that we've looked at two problems, one involving series, one involving parallel equivalent resistance, what we can do is analyze a mixed circuit using our understanding of equivalent resistance. So what our goal here is to calculate the equivalent resistance for this circuit. It's a pretty complex circuit, but what we're going to do is break this thing down using our understanding of equivalent resistance. So if we take a look at the circuit, what we have here is we could divide the circuit into series and parallel parts. If you look at these two guys here, these are connected in series. If we sort of just ignore, this red circle, you can picture your current flowing through the circuit. That would be considered a series circuit. This portion over here is a parallel portion of the circuit. You can see that they're connected in parallel. What we want to do is kind of break this circuit into two parts and use our formulas accordingly. So what we're going to do first is we're going to pick on these three resistors connected in parallel, and my goal is to consolidate these into a single resistor using my equivalent resistance formula. Okay, so what I'm going to do is I'm going to show you how that looks. What we do is we take our equivalent resistance formula for parallel circuits. We simply plug in our resistances, which were given in the original problem. So we have 75, 50, and 30. Same as in the example I showed you earlier on the board. We're going to find a common denominator here. If you need a little bit extra help with that, just feel free to pause the video and think about it. We're really just trying to find a common denominator between three numbers, which happens to be 150. We've got a common denominator. We can add our fractions straight across. We can flip our fractions, and we can solve for our equivalent resistance. So we end up with 15 ohms. Now, if you think about what this represents, we've combined our three resistors into a single resistor, essentially, with 15 ohms of resistance. So I could redraw my circuit from this one to look like this. Okay, you can see I've still got my original R1 and R5 resistors, 12 and 18, and I've got a new resistor that represents these three sort of consolidated into one equivalent resistance of 15 ohms. Okay, so I've redrawn the circuit. I've now got a simple series circuit, which allows me to use my equivalent resistance formula for series circuits. So you can see what I've done is taken R1, I've taken my new resistor that's been consolidated from my parallel branches, and I've added it to my 18 ohm resistor to come up with a equivalent resistance of 45 ohms. Okay, so that's really the end of the tutorial. Hoping this helps you understand equivalent resistance. This can be very useful moving forward as we analyze complex and mixed circuits a little bit further. All right, thanks for watching.